This is GATE 2010 question number 18, which states that an insulating sphere of radius A carries a charge density rho r is equal rho naught a square minus r square cos theta. This is the charge density which is given, volumetric charge density, where r is less than a. The leading order term for the electric field at a distance d far away from the charge distribution is proportional to. So to understand this, let us come to the question. So whatever is given. So given thing is that charge density of insulating sphere of radius a is given as rho of r, which is rho naught a square minus r square cos theta, where r is less than a. A is the radius of the sphere which is given. Now what we need to find is the leading order term for electric field at a distance d from the center. That is what we need to find out. Now we already know that if theta lies between 0 to pi by 2, then cos theta is greater than 0, because cos 0 is 1, cos pi by 2 is 0. So in between 1 to 0 the value fluctuates, whereas from pi by 2 to pi it fluctuates from in the negative sense, that is 0 to minus 1, because cos pi is minus 1. So this is an important point which we have seen, which we know. This is an important thing. So intuitively we can see that from this particular thing only we can tell that half part of the sphere will be positive, half part will be negative. So net charge in the sphere is 0, but the dipole moment will be non-zero. So this kind of configuration will be there, where this is your theta. So theta from 0 to pi by 2, you will have some positive charges, that is the upper hemisphere, whereas the lower hemisphere you will have some negative charges. Here only the quadrant of a particular sphere is being drawn in order to visualize the thing. But we can also prove that whether the charge is 0, net charge is 0, and the dipole moment is non-zero, we can prove it. So let's come to a small proof. So Q is what? It will be charge density times the volume element of the sphere, and we know that the dV of the sphere is r square sine theta dr d theta d phi. This is known to us. So rho, as per given, rho naught a square minus r square dr sine theta cos theta d theta and d phi. This is what we have. Just put the d phi dv here and open the row which is given in the question like this. I have just written it here like that way and separated the integral of r, theta and phi. This should go from 0 to a and so on. But if we only look about this particular integral sine theta cos theta d theta, I multiply by half and divide it by 2. So what happens is that it will be 2 sine theta cos theta, which comes out to be sine 2 theta. If you integrate it from 0 to pi, this will come out to be 0, because sine 2 theta d theta will give you minus cos 2 theta from 0 to pi, and that will give you 0. Therefore the entire thing becomes equal to 0. That proves that the net charge in that particular sphere is 0, because as we have seen that because of this theta term, theta from 0 to pi by 2, the cos theta is greater than 0, cos theta is less than 0 for the pi by 2 to pi, which I have already showed that upper part of the hemisphere will be positive, just like this, and the lower part will be negative. Hence the net charge becomes 0, equal and opposite. But what about the dipole moment? See, we can prove that the dipole moment is non-zero. How? Dipole moment is defined as some p is equal to r dq, where r is the radial direction, the distance, any distance in the radial direction, some arbitrary varying distance. So r. So how we can define r? So in the spherical polar coordinate system, r is defined like this: r sine theta cos phi I cap plus r sine theta sine phi j cap plus r cos theta k cap. So this is what we define generally, the r vector. And rho is given in the question. So we just write in the I cap direction, in the j cap direction and the k cap direction, like just the integral. And in the same way, the r is varying from 0 to a, theta varies from 0 to pi, and phi varies from 0 to 2 pi. Similarly, in the k cap direction, 0 to a, 0 to pi and 0 to 2 pi. This is just for to understand that the dipole moment will be non-zero. So if you just take the I cap direction, j cap direction one by one and k cap direction, I've just written it. You can always see that. Just I have written this r in the I cap direction, so it will be just r sine theta cos phi, rho naught cos theta is already there, and there will be some a square minus r square term, and this is the volume element dv, r square sin theta dr d theta d phi. Similarly, I have written for all the other directions like j cap and k cap. In the I cap direction, if we focus only on the phi integral, d phi integral, we have one cos phi and d phi. Cos phi d phi from 0 to 2 pi comes out to be sin phi from 0 to 2 pi, which gives you 0. Therefore, the entire I cap integral becomes 0. Next, so this will have a plus sign and this will also have a plus sign. So now j cap integral is having sin phi. This sin phi is there with d phi. If you integrate sin phi d phi, it becomes minus cos phi from 0 to 2 pi, again gives you 0. So the I cap dipole moment is 0, j cap dipole moment is 0. Only thing which is left is the k cap. Let's see whether the k cap dipole moment is 0. There is no phi term here. In the k cap integral, if you see, there is no phi term. So d phi, if you integrate, it will give you 2 pi. In the theta term, you have sin theta, cos square theta, d theta. This is the integral from 0 to pi, which we generally integrate. And 0 to a, we will integrate this particular term, that is r cube, a square minus r square dr. And rho naught will be in the outside because it's a constant. So if you integrate all these things, it comes out to be a non-zero quantity in the k cap direction. It comes out to be 1 by 9 rho naught a6 pi k cap. Forget about the calculation, whatever is the calculation, but ultimately the main intention is to show that the dipole moment is non-zero. So main thing is that here the dipole moment is non-zero, but the net charge is 0. That is what I tried to show. So if the net dipole moment is non-zero, in the k cap direction there is a finite dipole moment, non-zero dipole moment, then the electric field at some distance d, okay, some distance d will be what? Will be due to the electric field due to the dipole, because dipole moment is non-zero. Therefore, the electric field at some distance d will be definitely due to the dipole, and we know that the electric field due to the dipole, whether it's an axial position or equatorial position, it's always proportional to, the electric field is always proportional to the distance cube. So this, since it is given in the question in terms of d, so electric field due to dipole will be proportional to d cube, inversely proportional to d cube. So it will be d to the power minus 3 will be the correct option for this particular question. So the main thing in this question, based on this charge density, we can comment that half of the hemisphere is having positive charge, half will have negative charge. Hence, it is having equal amount of positive and negative charge, makes the q, which we have already solved using integral, as 0. But at the same time, we have also shown that the dipole moment is non-zero, and particularly in the k cap direction, we are getting some non-zero dipole moment. So since dipole moment is non-zero, therefore at a distance d from the center, the electric field will be due to the dipole, and we know that electric field due to the dipole is the leading order term in the electric field due to the dipole is generally proportional to or inversely proportional to d cube. So therefore it is d to the power minus 3 is the correct option for this particular question. So let's come back to the question. D to the power minus 3. So the far away from the charge, the leading order term of the electric field at a distance d far away from the charge distribution is proportional to d to the power minus 3. This should be the correct option for this particular question. Thank you.